You again for the invitation. It's great to speak to some of these amazing material science and engineering graduate students here at NTU. Today, we're going to talk a little bit about some materials challenges and somehow structural aspects. This here is basically Canada in a nutshell, and Alberta is located over here in this region. Just get a pointer here. Okay, so basically Edmonton is where our university is located, which is this little star right here. And often at times in the late evenings and so forth, you can see the northern lights. And we have some really nice parks, national parks, Jasper and Banff. So if you ever come and visit out in Alberta, you can see some of this. This is what our campus looks like in the summertime. And then in a few months, or basically in about a month or so, this is what our campus will look like fairly soon once the winter rolls in. So our research group basically uses extensively solid-state NMR techniques and a newer technique called dynamic nuclear polarization, which I'll talk a little bit about. And so that's the core area that we specialize in. And then we basically use this method to really understand a variety of materials typically related to sustainable energy. So whether that's energy harvesting or energy storage, or basically sustainable lighting. We're looking at perovskite solar cells. We're looking at a variety of metal halide light-emitting diode type systems. And we've recently, or more recently in the last couple of years, starting to look at more sodium-based ion electrolytes for sodium-based batteries. And we deal with a lot of nanomaterials as well. And then in the past, we've done some biomaterials, but we don't do nearly as much as that nowadays. This is what our facility looks like or is comprised. This is our dynamic nuclear polarization magnet here, where you have a 614 Tesla magnet with a gyrotron. I'll talk about this later. We also have 5 other spectrometers in-house that we use to assess a variety of things. And we can go actually, our sample temperatures, we can run our experiments basically from 100K to about 900K. So we can actually look at what's happening as a function of temperature and so forth, okay? Now, some of you may be fairly familiar with metal halide perovskites. Some of you may not. So I just thought I'd show this overview here of the interest and why we spend so much time on them. And so what has happened over the last 10 or 15 years is this relatively forgotten material, in particular methyl ammonium lead iodide, exhibits basically really nice semiconducting properties at the appropriate band gap, roughly 1.5 eV, where you can demonstrate that you can actually have solar energy conversion. And then, of course, over the last 15 years or so, this initial discovery of about 4% or so is now nearing about 26%, depending on the composition and the day that you look at the measurement. And so the idea behind this is if we can transition from the classic standard of silicon, which has a very large energy payback time. At least in Canada, it takes us about 7 to 10 years to pay back the investment. If we can transition this to something like metal halide perovskite, we're able to potentially have a payback time about 65 to 70% faster. And so if we can learn how to stabilize these systems and understand how they behave, we can then adapt these for better technologies, okay? In this talk, what you're going to see is you're going to see a little bit of our work on lead, but we've also started shifting towards lead-free systems, and I'll talk a lot about that in the second half. And so this is the example here of why we're looking at tin and tin germanium, is because what you can see here is the lead is performing fairly well, but once you start incorporating tin, the photoconversion efficiency has decreased. And amongst to this, not only is it related for solar, there's also a lot of interest, what I would necessarily say perovskite-inspired materials. So these are systems that are often called perovskite, but they're not. And like you have them as light-emitting diodes or maybe lasers or what have you, okay? So what is exactly a perovskite and what's a perovskite-inspired material? So a classic perovskite is defined as an ABX3 type system where you basically have the B at the corners of each cube or pseudo-cubic type structure, where you have now a halogen sitting between those, and then you have this cube octahedral void space, if you will, where you have this green cation. And so the A site which is typically a monocation system such as cesium, or an organic system like methylammonium or fortiminium, can sit in this region here. And then you can substitute the B sites at the corners for lead, tin, or germanium. So you can think of group 14 type systems. And then, of course, your halogens can be chlorine, bromine, or iodine. The fascinating thing about this is these basic building blocks, if you will, you can then go into perovskite-inspired systems. And the idea behind this is whether they're looking for specific optoelectronic properties, you can basically use a perovskite, or you can modify this and start adding different valence ions across the periodic table and do some other tricks to go into a 2D sheet-like system, perhaps a 0D-like system, or a double perovskite, which is located here at the bottom here. And if you knock out all the green ions, then you can go into a vacancy-ordered perovskite like system. And these are the different ways that we can manipulate the optoelectronic properties as well as the physical properties of the materials, i.e. the degradation pathway. One of the key leading things is whether we can get away from lead. Now, in addition to all this very fascinating and elegant chemistry that we can do, we can also now start changing the crystalline size. And so going from bulk microcrystalline systems, we can actually now degrade or basically chew these up and go into the nano regime, all right? So now you can make nanoparticles of these materials, and you can passivate them with different ligands. And this brings out a new, photoluminescent properties, but also a lot of questions on the overall structure. And so this is the meat and potatoes of what we're looking at. And why do we choose NMR, right? I'm sure many of you will be like, well, the classic approach for structure characterization in at least semiconductors and solid-state technologies is X-ray diffraction or diffraction-based methods. And we do use diffraction-based methods. They're really great at understanding the average long-range structure, the morphology, what's going on. The challenge is when we start doing ion substitutions or dopants, or we start getting degradation products, because they're not periodic, or because they're very low concentrations, or they're only occurring at the surface, they're often invisible to diffraction-based methods. NMR, on the other hand, is a direct and isotope-specific technique. So whether it's ordered or disordered, we don't care so much, but we can see it. In addition to that, it's both qualitative and quantitative, and it's non-destructive. So when these things start to form, if they form in situ or ex situ, we're able to analyze them a little bit more readily. And then if you go into some more advanced techniques, which I'll show a little bit later, we talk about multi-nuclear or multi-dimensional methods. So just like in organic chemistry, you would look at carbon and proton NMR, you can do multi-nuclear systems and look at materials under the solid state. And they're only really worried about the local or medium range structure. So what I mean by that is basically the first or second coordination sphere. We're looking at somewhere between 3 to 10 angstroms, okay? And we can add different variable temperature abilities, and that helps us look at dynamics as well. So NMR not only can tell you something about structure, but it can also tell you something about dynamics. And we use a variety of NMR interactions to deconvolute this. I can tell you more about those later if you have some questions, but for right now, we'll just bypass that. Okay, so what I wanted to start with is trying to tell you a tale of 3 stories on group 14 systems. Okay, and this is kind of how we got involved into this. And the prototypical leading lead perovskite is lead-based. And what has happened traditionally is when you looked at methylammonium-based systems, they would often degrade into a variety of salts and monohydrates. Okay, and we learned a lot about this. And one way to fine-tailor this or fine-tune this stability is through a synthetic approach, but also through an ion mixing approach. Okay. And so again, we go back to this basic structure where you have a variety of possibilities in the A site and the X site. And in this case, we're going to look at X site substitution, looking at chlorine to bromine and then bromine to iodine. And the idea behind this is can you basically influence the optical band gap across the whole series? And then can you further induce stabilization? And can you control domain formation through different synthetic techniques? Okay, so this is work done by Dr. Carmaker, who's now at the University of Cambridge. He looked at this during his PhD, where he basically said, okay, let's look at a solid solution using a variety of chemical techniques such as solution synthesis, low energy ball milling, and high energy ball milling, and assess whether or not we can see differences in the overall structure. What we have here is a summary briefly, and I'll explain what you're seeing here. But what I want to draw your attention to is if you look at the red spectrum here, it's uniquely different from the green spectrum here, which again is different from the blue spectrum. Okay, and there's reasons for this that I'll go through in a little bit. All right, so the synthetic approach definitely changes the composition. Okay, what ends up happening in this case is when you start looking at a parent compound and you decide to substitute, if you look at this blue site here, you decide to substitute, let's say you have bromine rich and you add a little chlorine, or you have a chlorine rich system and you add a little bit of bromine. What ends up happening in the lead NMR is you have this parent peak here, and then you get a new chemical environment here. And so what you see here is you have a substitution now at one of these positions. So what it's telling you is that the lead chemical shift now is highly sensitive to the overall local lead environment. And this is really important because if you have homogeneous systems or heterogeneous domains, you can imagine to get different types of populations, okay? And so this is the first demonstration here that you can use lead NMR to actually assess whether or not you're getting really well halogen mixing. Now, if we take this and we go across the whole chemical composition of a solid solution, from chlorine-rich phase to bromine-rich phase, what you actually see here is the optical band gap changing as a function of bromine concentration. You see the unit cell expansion, again, as you increase bromine. Chlorine is a smaller anion than bromine, so you would naturally expect an expansion of this. In the lead NMR, what you see here is as you substitute chlorine out for bromine, you get these new chemical shift reference points. Okay, so systematically what you can do is you can go through this using different fields, different fitting procedures, and you can assess whether the system is homogeneously mixed, no domains, or heterogeneously mixed. So what you see here is in the solution synthesis, based on the kinetics of the crystallization and the thermodynamics, you actually get a chlorine-rich phase forming here. And so you have a domain that's chlorine-rich and a domain that's bromine-rich. When you do low energy ball milling, you actually see the 5 unique chemical environments. 2 of them are slightly hidden here. And this is due to a fact that mechanically, you average out all the chlorine and bromine throughout the composition. If you change this to high energy ball milling, you get the same overall distributions, but you get a broadening. And this is because the high energy and the soft lattice of this lead halide basically deform slightly. They're not amorphous, but locally they're disordered. Okay, so the synthetic technique does matter in these systems. Now we can go one step further here. When we were working at this a few years ago, there was a lot of discussion on whether or not the halogens are actually moving in space. So what this is a 2-dimensional XC experiment, exchange spectroscopy, and what it's looking for is it's looking for basically atomic level movement in the system that's rearranging the chemical environments. And what you can see here at short mixing time, so 10 microseconds, 50 microseconds, and 2 milliseconds, what you can see now is that the lead at the 4 site and the lead at the 5 site is actually demonstrating some type of exchange. What this exchange is, it's the chlorine and bromine ions rearranging in the lattice, going from this site to this site. If we increase that mixing time, you can see it more clearly where you have 4 and 5 interacting, you have 3 and 4 interacting, and you have 2 and 3 interacting. So what this is telling you is at room temperature, doing nothing at all, the actual halogens are rearranging in the lattice itself. So not only do you have the dynamics of the organic cation, but you also have halogen dynamics. Okay, we can then propagate this further and try fortimidium and cesium. Cesium is a smaller A site, fortimidium's a larger A site, and methylammonium falls in between in terms of the overall size of the cationic size. What you see for fortimidium and methylammonium is you actually have fairly rapid exchange of the halogens in that system, and they're fairly mobile. It changes, though, when you go to cesium. And the idea behind this is when you go to cesium, now the unit cell basically compresses itself and the lead halide octahedra tilt. And so we believe that this compression and tilting basically lock the halogens in place, and you don't see any halogen exchange occurring in the cesium-based systems. Okay, so that's kind of a unique feature of the all inorganic species. Okay. Now, before this, we learned that methylammonium lead iodide can degrade, and so what we wanted to push into is, can we go from lead to something that has no lead in it? And the reason for this is when we discovered that you basically form lead iodide, which is water soluble, and you can form a hydrate version, which then degrades to lead iodide again. If we can remove the lead component, we don't need to worry about the chance of lead leaching into the soil and then being absorbed through the ecosystem, whether it's through plants and animals, and worrying about these types of things. So what we transitioned to is lead-free alternatives. We spent a lot of time on this, and I'm not going to show you all this, but I want to just emphasize a few different things. Leading the lead space here, we got into a variety of double perovskites and vacancy-ordered perovskites, and learned a lot of unique things where if you do certain transition metal dopings, you can basically get 1 to 1.5 EV band gaps for these typically high band gap systems. Do some unique aspects where you can get white light emission. Okay, so there's a variety of things we can do that, and we can tune that white light emission from a warmer light to a cooler light depending on the additives we do. What we went here, though, is we decided to go into a tin or a germanium-based system, working ourselves up the overall column of group 14. So tin perovskites, the issue with this is I call these the understudied systems. If you have lead perovskites being the overstudied systems, tin are the understudied. And I think there's a lot of potential in the tin perovskite systems as they've evolved quite rapidly over the last 5 or 6 years from roughly 8% photoconversion efficiency to roughly 15% photochemical aversion. The problem with that is the degradation still. So instead of them breaking down into their constituent salts like lead, they have a tendency or propensity to oxidize, okay? And let's take a look at this. So if we actually look at lead, tin, and germanium as an NS2 type system, what you can tell really quickly here is you have these 3D and 4D orbitals, but with lead, it's a little bit unique. You have the F orbitals as well. Okay, so you have this lanthanide contraction aspect from the F block. This improves the 2+ performance. Here's the Frost diagram. You can see an oxidation state of 2 for lead here, and an oxidation state here of 4+. So you can see that there's a preference to be in 2+. Whereas for tin and germanium, it's a little bit more even, right? So that they have a propensity to oxidize quite readily overall, okay? The other part is you have this inert pair effect as you go down the column. So again, lead basically holds on to those s electrons more tightly. So in terms of the ionization energy, it's a little bit harder to kick them out, whereas it's a little bit easier to do that for tin and for germanium. So that's kind of the challenge now. It's a little bit of a different space we're working in. Now, a few things with this that we had to learn over time, and I like this little cartoon here because this is work done by Michelle, who spent a lot of time trying to figure this out, where the frustration was quite high, and it was because we could never actually formulate a pure phase of this methyl ammonium tin iodide. And what we learned after about a year playing with this is you have to be really careful both with how you handle the material, but also what you source as your reagents. What we were learning was a lot of the chemical suppliers that we were buying our tin 2 iodide from actually had a substantial amount of tin 4 iodide. Okay, and this is actually quite challenging to differentiate in diffraction sometimes, but it's quite easily to differentiate from solid state NMR. In addition to that, you actually have the onset of rapid decomposition. So what we learned is if you make this under an atmosphere using hypophosphoric acid and nitrogen or argon gas, is you actually get the nice cubic methyl ammonium tin iodide phase. But in situ, in the actual spectrometer, under inert atmosphere, you actually start seeing degradation after a few hours. This is just tracking the chemical shift and the full width at half max over hours. And if you wait long enough, let's say a couple of days, what you get now is you get this really broad peak that spans nearly 4,000 ppm. So you get this really weird disordered system, okay? What we've also learned was we've actually expanded the chemical shift range. So if you think of carbon, we know that most carbon signals will show up between 0 and 250 ppm, okay? In tin NMR, so tin 119 NMR, we were under the impression that most systems show up between minus 2,500 and 1,500, so about 4,000 ppm. And then you have tin metal here around 7,500, okay? What ends up happening, though, is when you oxidize this to a tin 4+ state, you actually start seeing now signals that are around minus 5,000. So you actually have about 1 to 1.2 megahertz, or over 10,000 ppm chemical shift range for tin, which is huge. So that gives you the potential for having high resolution data. Okay, that's really important. Okay, so how do we stabilize this? Well, if we take some tricks from the lead, we know that if we replace the organic hybrid systems with an inorganic cation, we can pseudolily instigate a phase that's more stable. Okay, the challenge here is the cesium tin bromide is cubic at room temperature, but the cesium tin chloride is monoclinic at room temperature. And so if you want to make a solid solution between these systems in a single cubic phase, we have to basically assess how do we trap this high temperature cubic phase at room temperature, okay? Because something has to be completely reconstructing. What we did, we took a little bit of an idea of what Canadians often call the polar plunge. And the idea behind this is if you take the perovskite and you heat it up to about 573 K, and then you cool it rapidly, you're quenching the structure. You're not melting it, you're not creating a glass, but you just quench the material quickly at high temperature. You can basically trap a metastable phase of this cubic phase right here. And then as the time goes on, day by day, you start growing in a little bit of that monoclinic phase until about 2 or 3 months later, you have a predominant phase of this monoclinic system. So we know that we have basically about 20 days to deal with this material. And that's enough where we can basically use a cubic chloride phase and a cubic bromide phase and start making a solid solution out of these. So here's your diffraction data. You can see they're all nicely cubic across the whole compositional series. This is the color changes where you go from this yellow to this nice black-like system, which is about 1.8 EV. That's really advantageous for a tandem-like device. So traditionally, if you just do a single junction, you're looking at around 1.4 to 1.6 with a perovskite. When you do a tandem device, whether you want silicon perovskite or a perovskite, you want something in that order of 1.8 to 2.2 EV. So we have that ability to do here, okay? So that's nice and knowing that. Now, what does the NMR tell us? This is kind of interesting. So what we saw is instead of we seeing this really nice clear shift like we saw in the lead, you have this parabolic chemical shift with cesium NMR. So what ends up happening is when you have a chlorine-rich phase and you go to 50-50 bromine, you see a change and you can say, okay, this might be due to the unit cell expanding. But then all of a sudden you have this contraction again where it comes back. And the idea behind this is it's a non-additive effect of next nearest neighbors. But there's something else going on. Now, what that something else is we're looking at basically tin NMR. And what you can see here is as you increase the bromine concentration, you don't actually see multiple sites. If you remember the lead example, we saw these multiple chemical environments where we can indicate different lead halide octahedra. We don't see that in this case. The reason for this is you actually have very rapid halogen exchange. Okay, so when you go from lead where you have, let's say, moderate exchange on the order of microseconds to milliseconds, now we're on basically halogen exchange on the order of picoseconds. Okay, so what ends up happening is on the NMR time scale, those halogen ions are rearranging, so you get an average chemical shift. Now, this is interesting because if you do now variable temperature over this and you measure the relaxation, you can actually plot and get the activation energy of this process. And what it ends up being is your activation energy is about 0.3 EV or roughly 30 kilojoules per mole, okay? And what ends up happening then is that this isn't a metallic conductor, but it's an ionic conductor. And this is due to the fact that you have bromine halogen ions moving around the system quite freely. And this is actually consistent with other metal halide ionic conductors in terms of tin bromide or lead methyl lead iodide or tin iodide itself. And so this basically opens up a new class again of potential sodium ion, sorry, not sodium ion, potentially tin halogen ion conductors. Okay. In terms of decomposition, this is kind of neat. Using diffraction, you only ever see the crystalline phase of the perovskite here. But when you start using NMR, both cesium NMR and tin NMR, what you begin to determine is you actually degrade this system into a 4+ state of both the cesium tin bromide vacancy ordered perovskite and this tin oxide that you don't see through diffraction because it's either amorphous or it's nano crystalline. Okay. Likewise, you can form a little bit of tin bromide. Previously, they indicated that you form tin metal. What we determined is you actually don't form tin metal as a degradation product. You have to be really, really careful again of the materials you source. Just like I hinted to when we did the iodide phase here, where you get this mixture of tin 4+, tin 2+. If you buy tin bromide from a variety of suppliers, tin 2 bromide, what ends up happening is you have a metal impurity. And because these are made through high temperature processes, that metal impurity persists throughout the whole system. And that's what's actually giving rise to the metal peak, not the fact that it's basically reducing to tin metal. Now, to further stabilize this, what we can play with is we can, instead of looking at the A site or the X site, what we can do is we can replace the B site. We know that lead and bismuth are quite exchangeable. They're relatively on the order of the similar size. We know we can make lead tin mixtures. And we wanted to see if we could further improve the stability of the system from oxidizing. I'm not going to go through all this data. I want you to focus here on this bottom corner here. This was done by Madu. And what you can see here is if you have the cesium tin bromide, which is a really nice potential material for a tandem type device, what you can see here is that after about 7 days, you go from this black phase to this gold phase. And this is basically due to a variety of oxidation products, both the vacancy ordinance system and the oxide. However, if you incorporate 10% bismuth into these materials, you can see that you have a tin that's only with tin neighbors, and you have a tin with a bismuth neighbor that's defined here, okay? But you can see that the black phase stays fairly stable, the NMR stays fairly stable, and the X-ray diffraction doesn't change at all either. So this is indicative of if you go from a hybrid system to an inorganic system, and then you further dope it using a 3+ heterovalent cation, you can really push the stability of these materials. Okay. Can we go further yet? Can we go to germanium? We can. I'm not going to spend too much time on it because it's quite a complicated system, but I wanted to emphasize the different types of NMR spectra that you can get. To date, what we've been talking about is basically systems that are either spin half or behave like spin half. So what I mean by that is they behave like carbon and proton. But you can also have quadrupolar nuclei. Germanium is a quadrupolar nucleus, and what ends up happening now is you get this huge anisotropic effect that when you deviate from cubic symmetry, you get these very weird broad line shapes. This is only a single germanium resonance, but you have a second order quadrupolar line shape to this. And when you go from this near cubic system to a less cubic system, you can see that line shape basically changes, okay? And you can look at basically how the bond distances are different. You can see this is a very strained environment. This is more of a cubic environment, and therefore it's receptive to that overall strain. Now, in addition to that, you get this unusual chemical shift effect. So what does that chemical shift effect look like? Okay, so what we learned looking at a body of these data, looking at 2+ and 4+ systems, is you actually have this inverse normal halide dependency. So what happens is if you have a normal, or if you have the perovskite 2+ system, an NS2, you always see, whether it's germanium, tin, or lead, you see this inverse halide dependency. So the iodine is actually found to highest chemical shift. Okay, so the most or least electronegative is actually found up to high frequency here. And the more electronegative is actually found to lower frequency. If you rip those two electrons off and you oxidize these systems to a 4+ oxidation state, you see a reverse. You see the chlorine now being at higher frequency, and you see the iodine at lower frequency. This influence is actually due to a spin orbit coupling. So normally we talk about NMR in terms of paramagnetic and diamagnetic components, and the paramagnetic component typically dominates where the chemical shift will show up. In the case when you go to a 4+ oxidation state, you also have a sizable spin orbit coupling. And this spin orbit coupling influence actually dominates over the paramagnetic, driving this exchange aspect here. And so this is kind of a really nice, elegant example of more of the physics or more of the electronic structure of what's going on. Okay, so that finishes story number 1. What I want to go to story number 2 is let's go away from microcrystalline-like systems and let's look at nano. Okay, so we have size-dependent properties, we have synergistic effects, we have an organic layer of passivated ligands, we have an inorganic core of nanocrystalline compounds, multiple different ions, right? We have an anionic system, we have a dication and a monocation system, and then we have different passivating ligands. And what we don't really know is how the overall structure is occurring here, okay? So, sorry, 1 second here. So what ends up happening is we got to look at this surface, okay? Again, I said that NMR is a surface technique. This surface is where all the action's happening. We're not so concerned with the bulk area here. How do we do this? Okay, well, one way we can do this is basically looking at how the NMR tools can basically look at what is occurring when this type of ligand is placed at the surface. Now, this is unique ligand, okay, because this ligand here is a soy lecithin that's Zwitter ionic. So we actually have 2 charges now. The organic cation has a cation and an anion that can basically exchange with a cesium or a lead or a metal halide, okay? Now, all these materials are provided to us by our collaborators at the ETH Zurich, Maxim Kovalenko's group. So he makes these excellent nanocrystals for us, and he provides them for us, and then we do some of the variety of NMR techniques to understand those structures. So let's take a look at it a little bit more. So this work is done by Deganta. He recently just graduated, and he's off now at Grenoble, France. And what you can see here is he did a variety of studies looking at lead and cesium NMR and carbon and phosphorus and hydrogen. So these are kind of just like spectator spectra. We just want to see what's happening. So the first thing you can see here is as we go from microcrystals down to nanometer crystals, what you can see is that this bulk lead phase and this bulk cesium phase basically starts broadening out, and you get this broader underlying component here and this broader underlying component here. So what you have now is you have cesium and lead that are isolated into the core, and then you also have cesium and lead that are basically at the interface of the organic ligand and the inorganic shell. Likewise, here you can see the aliphatic chain of the carbon is really nicely resolved. This is demonstrating that that chain is basically moving or is mobile on the surface. There's nothing holding it back. But the phosphate group has some broadening and what's called CSA. What this indicates is that that site is actually binding covalently somewhere, or it's suggesting it's binding covalently somewhere. So this is important. The organic component is dynamic, but it definitely looks like the anion is actually coordinating to something. Okay. Now, because it's only the thin surface layer, one of the problems with NMR at times is its overall sensitivity. And the low sensitivity can be really challenging to get some of these nanoparticle systems. What we can do is we can induce a hyperpolarized state. And this basically allows us to manipulate the Boltzmann polarization and basically improve signal to noise. The way we do this is using dynamic nuclear polarization. So what ends up happening is you have the microwaves irradiating from one area to the sample that you've introduced some type of paramagnetic component. In this case, it's a biradical. So when these microwaves excite the biradical, these electron polarization can transfer to hydrogen. Now we know proton NMR is pretty easy. Electrons are about 660 times more sensitive than protons. So even if we can only transfer a little bit of this to this, we should get very large sensitivity gains. Just to give you an example, a sensitivity gain of 10 is about 100 in time. So you can imagine that if an experiment would take you 100 days, you can now do it in 1 day. Okay, that's the kind of things we're looking at. And then you take this and you transfer it to whatever you're looking at. So that's what we're going to be doing. Okay, this is our system here. This is what our setup is. This is our gyrotron magnet. Basically, there's a gyrotron tube inside this, and this is where the microwaves are created. The microwaves travel along this corrugated waveguide down here up into the NMR probe. The NMR probe is hooked up to this cooling system where basically the samples cool to about 100 K. And then basically we get these enhancements. So this is our new radical that we just published earlier this year. It's performing very well. It's giving us enhancements about 110. This is about a time savings about 12,000 in time. The red spectrum here at the bottom is if you just do a normal NMR experiment, and the black one is what you get if you do a DNP experiment. So you can see the signal gain is immense. Okay, this allows us now to do 2D NMR on these materials. So the question is how does this cation anionic Zwitterion system engage with this? What elements is it substituting, and where is it binding? So this is a 2D experiment. It's a little complex, but you have proton NMR on this dimension, you have cesium NMR on this dimension, and what it's showing you is that these protons on the aliphatic chains here are basically correlating right at the surface of the particle. So these protons here are seeing just this area here. If you look at the amine group here, this tertiary amide, right? If you look at that group here, that system is actually showing you at the surface, but it's also showing you subsurface. So what it's suggesting is that this system is getting into one of these environments. It's suggesting cesium is getting kicked out. Okay, and that's really important. All right. Now, we can now go to what's called dipolar recoupling. Don't worry so much about this figure. Don't worry about these graphs. What this does is it takes the through space interaction of phosphorus, and it's looking at what's near it in terms of cesium. Okay, so if you're looking at this, what it tells you is that these are experimental data. The colored lines are fits. If you look at this, we have something on the order of 9 to 10 angstroms. So if you go back to this structure, phosphorus is really far away from cesium. That's what it's telling you. Okay. If you look at proton and cesium, you can see that the protons in cesium, they're around 6 angstroms. Okay, so what that indicates is the cesium cations aren't really near the phosphate group. Again, reinforcing that amide might be kicking out cesium and replacing it. If we switch this now and we look at phosphorus lead, so what phosphorus is doing is, are there any lead neighbors near it? What you can see through these fits is that you do have a fairly good distance of about 3.8 angstroms. Now, these are binding modes that we did computationally. I'll show that to you in a little bit. But if we have this 3.8 angstrom distance, what this would suggest if you try to triangulate this is that the lead actually removes the chlorine, and you have this new covalent bond with oxygen. And if you measure a lead-oxygen phosphorus distance, you're on the order of about 3.5 to 4 angstroms. So what this is indicative of is that the cation suggests it's moving the cesium out. The anion is replacing chlorine and binding to lead. Okay, so we're trying to build the structural model here. Now, if we take our experimental results and we do some really nice MD simulations, these MD simulations were done with our collaborator Kovalenko with his group. We basically get 4 options here in terms of lowest energy performance. Okay, so you can have a system here where nothing gets cut off the surface, and you have the electrostatic charges here. In this case here, you have the electrostatic charges build where this cation interacts with this anion and it sits in the pocket, or vice versa. Or you have binding mode 3, where you basically cut that first layer off and you replace it with an organic cation. When you look at the overall binding modes, the energetics, and the data, the best fit of the structural model is this system here where you have the cesium leave the pocket, the tertiary amide sits in that pocket, and you have the chlorine coming off the lead, and you basically have this oxygen coordinating to the lead site. And that's the overall structural model that we believe is the majority of that system. And that was published last year in ACS Nano. Okay, in my final story here, that I just wanted to emphasize some of our most recent work. So shifting from perovskite-like systems in group 14 to nanomaterial perovskites, what we're doing now is we're going to vacancy-ordered systems, and we're looking at high-entropy materials. Many of you know in the last 10 or 20 years, high-entropy alloys have really taken the storm, and we're starting to use these and migrate this to oxides, halides, chalcogenides, other types of materials. Okay, so the idea here is we don't want to use perovskite, and we don't necessarily want to use double perovskite where you replace a 2+ ion with a +1 and a +3. What we want to do is we want to go to a vacancy ordered system. And the reason why we want to do this is now you're dealing with a 4+ cation. So the oxidation state is happy. It won't further oxidize. And if you look across the periodic table, both the main group and transition metals, you actually have a lot of options for 4+. So we can really emphasize the high entropy aspect of this. Okay, so these are the few of the ones we worked with. This study was originated based on a study that just came out of Nature 2 years ago, and I'll explain why we did that. So this study in Nature from a Berkeley group basically looked at a ink-based approach using the same type of parent compounds, a cesium metal chloride system, where they can incorporate up to 6 different 4+ cations into this. And what they indicated is that you can make single crystals that are high entropy. And they use diffraction. The diffraction data look good. And we say, okay, that's fine. But the question then becomes is when you have isoelectronic metals, and you have isostructural structures, how do you discern whether or not you actually form a high entropy material? Okay, so that was their question. This is our attempt at the same system. You can see here we get fairly similar results. And then we do a ball milling approach, and we're going to walk through this, okay? So in this case here, we actually choose cesium NMR again because cesium's sitting in that A site, and it's really sensitive to the 5 possibilities around it. So there's actually 4 B sites sitting at each cesium. And so you can imagine that cesium's kind of like that spectator. It's able to see everything happening around it. So when you take a metal and you change it, it should be able to report on this. Okay, that's at least the idea. So this is work done by Brian. Brian typically does sodium-ion batteries for us, but this was one of his first projects that he started. And what he wanted to do is he said, okay, how high can we load these high entropy systems from 1 element to 8 elements? Okay, so we'll call these We'll call this a typical compound. We'll call this a binary. Maybe we can call these medium entropy, right? This would be your high entropy systems, and maybe even call them, I don't know, super entropy. The point being, these are their high entropy, okay? He also wanted to look at the ink-based approach, but also hydrothermal to see if we can get better optical properties, and then also high energy ball milling. So let's walk through this and see what happens. So when you do the parent compounds, these are just simple one-site systems, zirconium through selenium. These are the electron micrographs of them. You can see they're fairly crystalline. These are the unique chemical environments. So although these are isostructural and the diffraction peaks will move the 2 theta value with either unit cell expansion or contraction, depending on the size of the B site, they're basically all in a very similar position. What you do see here, though, in terms of the NMR, is you have really nice cesium chemical shift dispersion of about 60 ppm. So from 90 to 150 ppm. This is really helpful. It's kind of a unique fingerprint for each system. All right. So what happens when you do a hydrothermal approach and you just start adding different metals? Well, you can see really quickly is all the X-ray diffraction looks very similar. Okay, so again, if we use the initial system, this hydrothermal approach would suggest that we actually form high entropy single phase materials just using diffraction techniques. Okay. Now, what's interesting though is when you actually look at the NMR, that's not what you see. So now this is cesium NMR of the exact same system. So these 8 systems here are demonstrated here. Okay. This is 8 elements, 7, 6, 5, 4, 3, 2, and a single element. So you have this parent phase that when you add a secondary ion, so tin to zirconium, you get now this distribution of different chemical environments. And what this different chemical environments is looking at is it's basically cesium sitting in the center, seeing, oh, okay, it has all tin, or it has 1 zirconia neighbor, or 2 zirconia neighbor, or 3 zirconia neighbor, or 4 zirconia neighbors, okay? And if you actually fit these data, you'll notice they're not binomial, all right? So because they're not homogeneously random, we actually have heterogeneity. So the X-ray says they're homogeneous, but the NMR is demonstrating that you have domains. So they're not a homogeneous system. Whether they're nano or micron is a different question, but you have domaining, okay? This is not shocking because we've shown in the perovskite phase, when you do solution methods, when you do mixed halides, you can get chlorine-rich phases. So similarly, you're getting some other zirconium or tin-rich phase. Now, if you do mechanical chemical high energy ball milling, again, you have these diffraction peaks that look very similar. They're broadened because you have that disorder. But what you can now see is you have a little bit more of a Gaussian-like nature in this, where you actually see different sites coordinating, and they're a little bit more homogeneous. They actually follow a binomial distribution. And when you go to higher loadings, you actually see very nice Gaussian-like line shapes that follow a normal distribution. Okay. Now, what's neat about this is if you actually use the chemical shifts that you have and you do a weighted average of the center of gravity shifts. So this is taking the isotropic shifts of these parent phases here. Okay, so you take the parent phases here, these chemical shifts here, and then you weight them based on the fraction EDX tells you is there, you can get a computed weighted chemical shift. And this can predict where you'd expect the center of gravity for a homogeneous system. We back this up in the paper with DFT calculations, where you can also demonstrate that you have a very nice relationship between the computed data, the experimental data, and the weighted data. And that's the indicative now that we have in this equation, where if you start with any type of elements, you can basically predict where you'd expect your chemical shift to be if it's going to be homogeneous. So this is a nice analytical tool now that you can use to assess, yes, I have a homogeneous system, or no, I have heterogeneity. To prove this, we had some interesting side effects here. If you take zirconia balls in your ball mill versus stainless steel, what actually ends up happening is you actually etch zirconia from those balls, and you get a chemical shift that you don't expect. So this line here that you see dotted is what we would use from our computed experimental result, okay? And you can see for stainless steel, you get it right where you want, but if you use zirconia, you get a shift, and this actually shifts towards the zirconium-rich phase, okay? And so this is indicative that you can also use this equation to predict if you get any impurities in your system, okay? I did some T1 data. I'm going to avoid that for today's talk because it's not relevant. But you also have some T1 influences on this. Interestingly enough, your relaxation actually gets very short once you enter your high entropy system. So once you add 5 elements or more, you actually get very fast relaxation, indicative of a highly entropic material. Okay. Okay, let's go back to that single crystal. So how was that initial study out of nature able to get homogeneous systems? Well, interestingly enough, here's basically a 8-component system. And what you can see here is you have selenium that basically phase separates on this, but the rest of the elements are fairly well homogeneously dispersed throughout the whole material. If you take these materials and you basically do a unit cell refinement on them, or sorry, a full single crystal refinement, what ends up happening is because you have so many isoelectronic metals in a isostructural system, you actually can fit them to anything. Okay, for anybody that's really experts in diffraction, this isn't shocking to you. But if you didn't know this, this is something that is happens quite frequently. So we did 4 different models using different constraints. So we constrained it first to the EDX results. We also constrained it to basically the EDX results of the bulk powder. Then we just said, okay, let's go very simple. Let's constrain it to only 3 elements, and then let's constrain it to only 2 elements. And what you can see is whether you have all the elements or only even 2 elements, your fit value is good for all of them. So what this is indicative of is single crystal X-ray diffraction may not be the most valuable tool in assessing a high entropy material, okay? But NMR seems to be a little bit more unique in that. So let's look at this system here. So we reproduce the synthesis approach for this, and then let's compare it to what we do using mechanical chemical. So this is the solvent-based B5. The B5 are these 5 metals. So this bottom spectrum is what you would get from this synthetic approach. And this top blue spectrum is what you get if you take the same material, but you do high energy ball milling. So what you can see here is that in the high energy ball milling approach, you actually get a homogeneous or a near homogeneous system with a chemical shift that you'd expect based on these 5 compositions. When you do the ink-based single crystal approach, the NMR tells a different story. You see that you have a little bit of platinum phase here, and then you have some mixed binaries. You have a little bit of tin telluride, and you have a little bit of hafnium zirconium. So what ends up happening is you actually don't get a homogeneous high entropy material. You get a domain-rich heterogeneous material that has metals in specific positions. You may still have some randomness, but the bulk of the crystal is actually still very much a binary or a ternary-like system. Okay. This is an example here. This bottom one is all the parent samples overlaid. This is your 8-membered system using a solvent approach. This is an 8-membered system using a hydrothermal approach. And this is an 8-membered system using a mechanical chemical approach. And what you can see here is you get these domain formations in the hydrothermal or solvent approach, but you get what you'd expect in terms of a high entropy material if you use the mechanical chemical. So the moral of the story here is if you do a mechanical chemical system approach, you can force these to form true high entropy materials. If you use a solvent-based approach, it's very challenging to do it. We have not yet been able to do it, but you do get these domaining systems. And what's interesting is the X-ray diffraction for all of these would indicate that they're high entropy, but actually at the atomic level, they're not. And this was just recently published. It's actually not out yet. It should be out in the next day or two through small methods. Okay, so to finish up, and I'm sorry I went 2 minutes over here, your solid state and DNP NMR, I hope I've demonstrated are robust and sensitive analytical techniques that can give you insight into stability, into structure and dynamics of basically metal halide systems. We looked first at the group 14 series here, where we have halogen dynamics that are very fast in tin, a little bit slower in lead, and we can stop this by tilting the octahedra by introducing a small cation. I hope I've also demonstrated that cesium, tin, and lead NMR are very receptive probes to looking at order, disorder, and surface species. We've also emphasized that you can expand the chemical shift range of tin to newfound levels, 12,000 ppm. All right, that's kind of a newer outcome in the last 5-6 years. You can also extend to quadrupolar. I didn't spend too much time on this, but you can do germanium. Germanium is a very challenging nucleus, and I can talk about it more if you're interested. But you can go into the halogens. We've done chlorine, we've done bromine. We've also done NQR of bromine and iodine, and other groups have done this as well. We've demonstrated that if you have an NS2 system, you have an inverse halide dependency. And if you oxidize these materials and rip off those, or you ionize those last 2 electrons, you have a normal halide dependency due to spin-orbit couplings. Your long-term stability can be improved by going into non-hybrid systems, so removing that organic system, and also through homo and heterovalent doping, okay, or substitution, sorry. DNP, along with dipolar recoupling, has helped us develop surface models of nanomaterials. And I really think there's kind of like these new opportunities in these high entropy systems using NMR techniques, okay? So I'd like to thank my current group right now, Arkady, Kishore, Christina, Brian, Amy, and Glorious. A lot of this work was done by our alumni, our excellent staff, our funding agencies here. And if you want any more information, you can take a scan of this. And I'm very happy to stop now and take any questions you have. Thank you very much for having me.
Thank you so much, Prof, for the interesting talk. Now we will open the floor for questions. So if you have any question, please feel free to unmute yourself and ask. Okay, like if no one have question, I have couple of questions. So like in case of stability, so the metal halide perovskites are not so much stable, right? So I'm like quite interested in how the sample preparation happening for solid state NMR, and like so so is it quite challenging to do the solid state NMR with like halide, because like halide is not stable, right?
Yeah, no, it's not too bad. So like we typically look at powders. So we in our group we normally just make bulk powders, but we have done thin films. We have done other materials where we have to manipulate them a little bit. For the ones that are readily oxidized, so let's say tin and germanium, we typically keep them under an argon atmosphere while we prepare the sample, and then we run them under nitrogen gas. So that helps delay the degradation process. So we have ways of controlling that to mitigate degradation. Yeah.
Okay. And like apart from like your most of the compound is halide based, right? So we can do only apart from halide, we can do only the selenide or like chalcogenides, right? These
Oh no, we
solid.
can do we can do all types of things. Like we've done like silicon, like silicon semiconductors, silicon only.
Okay.
We've done oxides. We've done chalcogens. Basically, any type of solid state material we can look at. It doesn't have to only be a halide or a chalcogenide, right? That's just our area of specialty. But we've done a lot of we've done, what was the other thing? We've done alloys. So like lithium bismuth alloy, a whole bunch of things, right? We've done metal organic frameworks like MOFs. We've done COFs. We've done zeolites. All those types of systems. So anything that's material related, we can handle. Yeah.
Okay. And can we go to slide number 52?
Sure. 52? Is that what you said?
Yes. So yeah. So here actually, in case of selenide and germanium, so there is no peaks, right? Like near 150. So why that is so? Like,
Oh, these ones here?
yes.
Yeah, that's because that like they are incorporated into the system, but they're very small amounts. So germanium and selenium are the last two. If you go here, they're like near the end of what we add, right? So and this is a hydrothermal approach. So what you actually see is you actually see a predominance of these elements, and germanium and selenium is not really incorporated to the hydrothermal ones. Okay.
So if you did it by like ball milling, so that should be incorporated, right?
Yes. So by ball milling, do I have them? Sorry, I'm trying to find. Oh, here they are. In ball milling, what you can see here is that this peak shifts closer to this regime. So once this is the area here where we start adding, and so you can see all of a sudden this peak is shifting this way. Oops, sorry. This peak is shifting this way as we add these elements into the material.
Okay.
Yeah. So this is how we use that knowledge to kind of generate this equation, and that's how we kind of vetted this aspect where we get this. And then of course we take this and we do EDX analyses. It's difficult because now we're at about 1.5–2% per metal. So we're at the detection limit, but we'll do line scans across the whole system and basically get an average composition. And sure enough, you have germanium in there. Selenium does go, but sometimes it does precipitate, right? Like we did demonstrate that selenium, for example, does precipitate out, right?
Yes. Okay. And like in case of pair distribution function, people are also doing the same thing, right? The local coordination environment. So like what do you think about in which one is better, or like is there in comparable with the pair distribution function or the solid state NMR? Yeah, I know like solid state NMR is like new kind of thing. I think people are now
Yeah,
doing.
no, I'm not here to say one method's better than the other.
Yeah.
I think NMR has a few tricks. Okay, so the unique thing about NMR is it's really looking locally and specifically, right? So you can use it kind of to help you decipher some things. The issue, one of the issues with pair distribution function for these types of systems is because you have B sites that are so similar in size, it's very challenging to, because you have a distribution, how do you constrain your fit, right? So this is an issue for everything, okay? But at least from the NMR side, we have different positions that we can use to say, yes, that's specifically there. Whereas with pair distribution, if you look at I'm not sure I have this, I don't have the graph, but the changes in crystal size, the changes in crystal size from, oh my gosh, where are they? Here, these parents, you can see that just from the slight movement of the 2 theta peak, they're all very similar in overall ionic size, right? I think I had a nice graph in the paper. I don't have it here, unfortunately, but I think we're all within 0.1 angstroms of each other, right? So it gets very challenging from that perspective. Whereas with the NMR, you have a little bit more difference. Not saying you can't use pair distribution function, but I think there are some challenges once you get to like 7, 8 elements. How do you know what is contributing to what, right?
Okay. And for like high entropy alloys, so if we have like zirconia and we are using zirconia ball, so I think you already mentioned it, but so can we just again mention? So is it better to using like stainless steel jar or something else?
Okay. Yeah. So if you can get it fairly quickly in time, the zirconia is not too bad. Okay. But if you have to go like for hours, like let's say 2 hours, then the zirconia starts to incorporate into the material. But stainless steel is not innocent either. Okay. So I didn't talk about this, but I'll just mention it because you asked. So you can see the relaxation here. Okay. So what happens is with zirconia coming in, your relaxation is around 9 seconds. And this is because all the elements here are diamagnetic. Now, if you use stainless steel, you don't really see a change in chemical shift, but what you do see is a change in relaxation. So you go from 9 and you go 2 orders down, you go to 0.09. Okay. What that tells you is you're still stripping a paramagnetic ion out of this. And because stainless steel has chromium and iron and molybdenum in a paramagnetic, or manganese in a paramagnetic system, what ends up happening is you still etch metals from that. Okay. And we confirm that looking at molybdenum. So we made a molybdenum one. And again, you can see that the T1s are on the same order. And so what happens is molybdenum is paramagnetic here. The iron, the chromium, and manganese are paramagnetic here. You are getting some etching as well in the stainless steel. So I think you just have to be cognizant that if you have to go for very long times, you could be introducing other impurities into your system that you're not aware of normally.
Okay. So like if anyone have no question, then I think like we can end here. So thank you so much, Prof, for the talk, and like so for joining today with us and sharing your research. And thank you everyone for attending and participation. Prof, like we will send you one certificate later. So for about this talk.
Yeah.
Nice
Thank you so much. Thank you for having me, and thank you for spending the hour with me. Have a great Friday.
Yeah. Bye.
Bye bye.